This is going to be like a halfway talk between the talks that were previous to this and the next ones. So everybody knows what DeFi is. The objective of the talk is to look at privacy and what really it means in terms of economic implications to DeFi as such. So if you were to look at DeFi stack, there have been a bunch of people who have been classifying things, and if you look carefully, you can see typically it gets over here. I don't know if you could hear me. It's over there. And I don't think that's the only place where you can actually have DeFi, privacy for DeFi. And I don't think that probably might not be the optimal place for that to exist. So the talk I'm going to describe, like, at least in my head, how I see privacy and how that, how you could actually see two worlds, one with privacy and one without privacy. And if you were to run two sets of machine learning algorithms to actually run arbitrage, how would that compete against each other, and where would be the arbitrage being captured? And I kind of look at the techniques that's available for us in the so-called DeFi world. Mostly I'm talking about zero-knowledge proof systems and things of that sort. Just comparing all of them and giving you a notion of like how much does it, loosely speak, cost for us, both in terms of computation, capital efficiency, and other things, price discovery. So you understand, like, what does really privacy mean in terms of, if you're running an application, you have a version of the application. Imagine a lending application. It doesn't have privacy. Say you need, take a random DeFi protocol that gives you a lending, or even DEX, right? Say Uniswap. Uniswap, 30 bips, right? 30 bips, you can operate at that level because you don't have privacy. Assuming you had privacy, I don't think you could achieve the kind of efficiency with 30 bips, because it's going to be more expensive than that. Right, okay, so I'm just going to talk about automated market makers. Again, most of the people in the room probably know what market makers are and how it works. Essentially, what I wanted to say was, if you were to look carefully at automated market makers, they have certain functions, and there are certain ways in which they work. So, okay. Ignore the bits. Like, let's assume very simple, AMM. Assume Uniswap, right? Uniswap V2, not even V3. So it's a constant function market making. So X into Y is a constant, and everybody knows what that means. And so this is what we are trying to avoid, okay? And this is very important. You need to recognize why this is important. So in a normal world, we always see who is actually putting in all the bits and who is actually the ask, right? Everybody knows this. So you know who got what for what price. Very, very important thing, right? And this results in this paper, right? So literally, this was like kind of a note published by these three guys. Tarun, everybody knows, Alex, and Guillermo. I believe Guillermo is here, and he's supposed to give another talk. So, what they recognize is, like, if you were just to think of this like as a normal equation and do a dy by dx differentiation, what you end up doing is, like, you get one side of this thing, right? Like, once you know the one side of it, you can actually go back and trace back, look at the wallets and know who it is, right? So any mechanism that you provide to provide privacy is kind of in a difficult spot. That's what this says. I'll walk you through the rest, right? So three things were kind of proposed. One is creating randomness in price. Second is batching, and third is like the trade-off. I'll kind of describe each of them in a bit of detail. Okay. Did I skip what's going on? All right, okay, fine. So batching, right? What do you mean by batching? Batching, we already have some of the mechanisms in a blockchain space to do batching. So if you look at rollups, more or less they are doing batching, right? So if you do batching with ZK, then by default you achieve two things. But now you ask the question, what is actually happening in there? Now you're getting an average. So one of the things that you recognize is when you have a curve, and when you extrapolate a curve, the point at which you touch the curve is a price discovery. When you get an average, instead of a curve, you have a straight line. Okay? You're straightening it up. It's like, think of like a circle, and you're looking at a circle under a microscope. You have pixels, and the pixels are on a line. So this is essentially what batching would mean. So essentially what that means is there's an inefficiency that's happening. So in theory, in a really microscopic sense, you could have a perfect circle that fits inside the circle that's been created. So there's an inefficiency gain, or inefficiency loss, whichever way you think about it, depends on which side of the game you're playing, right? So if you are inside, you're losing. If you're outside, you're gaining, right? So this is literally what I'm saying, right? And there's also this other problem, right? Imagine you have this challenge of having to run a strategy which is time critical, right? Now you have batching. Because you are in batching, you are not instantaneous in that sense. So you have a problem, right? Imagine you have a situation where you have a possibility of being front run, okay? Now you're in batching, your risk is much higher. I hope everybody understands what I mean, right? So, I was just as I was describing, if you think about secret techniques, by default, they have some amount of batching, and also they have some amount of ability to provide you with privacy, right? So you can actually get a lot of this by one shot. And I will talk a bit about GK towards the end. Right, okay, randomness. All right, randomness, again, think of this as a noise generation function, right? So I don't know if you recognize this thing called Dolby written on the side of various speakers. So what had happened is, like, a long while ago, 50, 60, 70 years ago, we were trying to record on magnetic tapes audio signals, right? And something that was noticed was that if you record it, there's a kind of a loss, so you need to put in a lot of white noise to fill it in, right? So you could almost do the similar kind of thing, not to the degree, but you need to have a very precise bound, right? The larger the bound, as I was saying, like, you can have a circle which is very jagged, or a circle that's almost smooth. If you look at it, it looks almost smooth, right? We want to get to the almost smooth thing. Then there's this question, how much of privacy do you want, right? How much of inefficiency are you willing to tolerate? So if you have, like, healthcare data, indirectly implied healthcare data, what I mean by that is, in DeFi, imagine somebody uses some protocol to get some pharmaceuticals, right? Or run some tests, right? By just looking at the test, you might be able to infer the state of their healthcare, right? To me, that is of high value. So in that condition, my circle would be like a circle with a bunch of spikes, right? I hope you understand what I mean. So that is what I'm kind of saying. Like, you have, like, a perfect circle internally, and there's a worst case out, and somewhere in between, you have various average cases. So this is the other mitigation strategy that this guy proposed. And then they actually proposed this. They said, you know what we could do? We could use differential privacy. So let me give a shot at differential privacy, and I kind of explain to you what really this means. I mean, just a bit of warning. I'm kind of proposing that, if you could actually solve one problem, the difficulty of solving the problem is equivalent of solving something else, okay? So probably this is kind of controversial, and you probably understand why I say that shortly. Okay, this is differential privacy. In general, it's very simple, right? Like, remember I was talking about batching? If you take batching, and if you actually make minor changes in there, and the overall statistical properties of that batch remains the same, that's differential privacy, right? And there are different ways to get differential privacy. Okay, that's effectively these are the things that are there. So you change the inputs, change the outputs, you do some randomness, all the kind of things that you normally would expect to do, but within a very tight bound, so that it doesn't really change the overall properties of the sample, right? So I also want to say something before I go into any more detail. So one of the most important things that anybody who thinks about efficiency need to recognize, in a very reductionist sense, right? In a complexity theory, in a very reductionist sense, if you think about a decentralized consensus protocol, especially a leader election protocol, one thing you need to note is you can actually think of this as a two-step process. The first step process is a decentralized protocol running a leader election protocol, right? The second step is whatever function you need to do in a normal centralized sense, in a logical sense, right? So imagine, like, you have a decentralized oracle. Let's assume that, right? What's the first half of the protocol is going to be? Assuming a leader election protocol. There will be a puzzle that's being solved among a set of 4 validators. One validator gets a chance, right? And the next step is going to be the real thing, right? So there is a delta. This is the key thing. There's a delta of inefficiency in doing anything decentralized versus centralized. So we need to be really wary of what are we trying to do. So if you are trying to get privacy and you're going to try to do it decentralized, you are 2 steps at disadvantage compared to a centralized thing. I'm just putting it out there so everybody understands, right? So, okay, right, yes, I'm kind of saying the same thing, right? So, and there is also some other cost involved, but I'm kind of making it very simple. So communication cost is not trivial, right? So when I say communication cost is non-trivial, it's like we always assume under all conditions that communication is almost zero. I mean, the cost of communication is almost zero. But at lots of times, the cost of communication ends up being expensive because temporarily, there's a value of time. So imagine you have going back to the conversation which I was saying, like imagine there was a transaction that need to happen really fast. And literally you have got this process now for you to go through to get to the result. You have a bunch of communication forwards and backwards that need to happen. So essentially what that means is if you were to find an insurance against the front running, that's a cost. Let's think of it that way, right? That's your insurance cost. If you're hedging it, that's a cost, right? Right, okay. This is the crazy construct that I've been thinking about. I mean, a lot of people have been thinking and I've been thinking. So I actually have a team and I build a protocol for providing privacy for DeFi. So one of the constructs you want to understand is like, you can think of privacy in some sense, that could go into the generalized mining bucket, right? So if you look at Lightyear, they're doing transcoding. Look at other people, Golem, if you think about it, they were doing distributed compute. This is, how do you actually provide, privacy, right? So generally speaking, imagine this room, right? Like imagine you had a Boolean detector over there detecting everybody who goes through this door, right? The privacy of the set of 4 people attending this talk is very much a function of how many people are in this room, right? That's pretty much straightforward, right? 1 by n in that sense. So you want to, incentivize people to come into this room, right? So how do you do that? So somehow one of the ways you do is you actually give incentives to people to participate, just participate. And you need to recognize there's a trade-off here. You can actually do a lot more compute versus incentivizing people to be in the room, right? I hope you understand. So I can actually add randomness to the whole thing. Adding randomness has a cost plus an error margin. So instead of that, I could just go the other way around, and I'm trying to find an economic solution where behavior has been altered by incentivizing people to provide privacy. This is kind of the general construct of generalized mining. Okay, so now I'm kind of trying to describe privacy in a slightly different sense, because most of privacy, what we see now, is kind of a second-order effect of things that has already happened. What I mean by that is like, we have Google providing search services, Facebook providing us with messages, ads, you name it, Amazon, supply chain optimization. Essentially, what is it that's happening? There's an arbitrage happening, or an adversarial game in loose sense of speaking, between an average user and an entity with a large amount of compute. I mean, I'm going to describe it in a bit more detail. But, the assumption here is like, what is the real gain they have, right? The real gain is situation number 1, Google with no indexes of my historical searches trying to serve me with ad and the revenue of ad from that versus Google with access to all my cookies and all my searches and providing ad content to me, right? This is the arbitrage between the two of them. And if you imagine this to be 2 curves, the gap between the 2 curves is the curve that we are really fighting for, right? And what we are literally fighting is like, okay, you as a human have an economic value. And this economic value is being kind of used by entities who have larger access to machine learning, hardware, and models, right? Data models and hardware, that's essentially what this means, right? So the argument here is like, what is the cost on the other side? Okay? So I'm kind of saying that we win as people who are interested in privacy if you could provide privacy for a cost less than this. Am I making sense? Okay, right, there you go. I call it the privacy disadvantage, right? Assuming 2 algorithms competing each other, one has privacy, one without it, difference between Broom is a privacy disadvantage, right? So this is what I was describing when I was talking about Google with cookies and without cookies, so not having my data, having my data. The difference between the two is a disadvantage, right? And the real question here is, how do you actually price this, right? How do you actually price this disadvantage? So this is the Google guys and the CMU guys talking about ML and how effectiveness of data and all those kind of things. So I want to add something more to this. So what I mean by more to this is like, there is an inherent cost for these guys to do what they do, okay? So I'm going to walk you through so you understand this better. So imagine you have a deep learning pipeline. You actually have a bunch of constraints. Firstly, you have a cost function. You can only at any point in time run so many machine learning models, number one. There's an opportunity cost, right? Number two, you have cost for running hardware. So energy cost plus depreciation cost. It's an asset that you are sweating, okay? Number three, if you want to randomly create models, you want to hire people who could build models for you and build and maintain models for you, okay? There's a cost involved. So assuming this is a very important construct to have in your head so you understand what this means in a larger construct. So if you were to do a model and you were to run an arbitrage in a machine learning sense, you also need to understand there are other competitors who are competing with you to doing almost the same thing. If there are two competitors at almost the same level, then the incentive for them to do a lot of these things is almost zero. They don't have an advantage. Okay, all right. Okay, so I was kind of thinking it from a data perspective, but it really doesn't matter. So I'll explain what this means. So if you do this, you could actually find the price of data, right? So you can think of price of data being as inverse function of privacy. What I mean by that is like if privacy exists, the security margin for any attacker on data is a function of the price of data. Does that make sense? Yeah, so, right, so yeah, I'm just kind of describing other things. But in general, in summary, this is what it means, right? So there are ways in which you can think of privacy in a slightly different construct other than just providing ZKs and other things, which is essentially being adversarial. What I mean by that is like you can have a GAN and produce synthetic data. And at times, if you look at Tor and other algorithms, they actually have synthetic data. In loose sense of speaking, that actually provides this kind of stuff. Right. Okay. Ignore all these pieces. So this is kind of thing that normally happens if you think about privacy and utility. We don't have a real curve like this. We really don't have, and it's very subjective and like it's kind of instantaneous. So given any data set, it might be anywhere at any point in time. It might vary as well. Okay, right. So this is kind of what I was kind of saying. Like this is, if you really have the ability to differentiate, price the data exactly, right? You kind of get a bound of differential privacy. Does that make sense? So the cost of actually providing differential privacy pretty much is equivalent of actually finding exact price of this thing. Yeah, I mean, I had a slide to describe adversaries and things like that and adversarial models. I will kind of touch on zero knowledge proof systems and kind of stop there. So, yep, in general, okay, let me walk. Who in the room doesn't know zero knowledge? Is there anybody who doesn't know? Okay, good. For the people who not here. So in general, it's a construct where imagine this room has one door and I make a claim that I have the ability to escape from this room without using the door. And then I'm the prover. Anybody who verifies me is a verifier. So this kind of a proof where I try to prove something to you, which my claim is true, irrespective of the fact that I try to do that as many times as you ask me to, but your knowledge of how I escape remains the same. It's called zero knowledge, right? So, yeah, so I'm just going to skip the rest of it. Generally speaking, we are more or less staying in the computational space, but you can have other ones as well. All right, so this is where I kind of come in and kind of talk about like, what's the cost of doing such things, right? I mean, I can compare like different flavors of it, and I can also look at how it looks compared to other ones. So forgive me for saying this, I'm more staying in the Ethereum space. So I was previously involved in the Ethereum Swarm, Orange Swarm team. So I kind of have a bias towards Ethereum. So, and I have my protocol deployed in Ethereum. So fully biased, acknowledging my bias. So the thing is like, if you look at the cost, you can see the gas cost, right? It's quite high, right? So if you really want to do privacy, it's high. The cost is high, the size of the proofs are going to be bigger, and the computational cost is also going to be big, right? So there is this cost that you have. And then sometimes you could actually use this to your advantage. Okay, this is just comparison between all the three major brands of it, Snark, Starks, and Bulletproofs. mean, there's been some, kind of merge between the snarks and the stocks. So what I mean by that is like, if you look at Halo 2, some of the things that are there, that the fry is being used to achieve some of the properties. So essentially, in a very simple sense, snarks require a setup. So whenever you want to do something, you need to run a setup. And the previous speaker was talking about Zcash. That was pretty much a problem with the setup. Its security is derived from elliptic discrete log problem. Stock doesn't require a setup. Security is from a random function, so it's kind of cool. Bulletproofs are like, is a kind of a zero knowledge for range proof kind of thing, where you could say, oh, I'm a set member, I'm a member of this group. And it's used in certain circumstances, certain protocols, not the ideal ones in that sense. So mostly I am kind of involved in snarks, I haven't done a lot on stocks. So this is my conclusion that I drew, right? Yeah, first and foremost is, like as I described, competing for price for a centralized system is going to be a challenge. So this applies to all the tech as well, right? So it is very possible that tomorrow we have FHEs and other things that actually significantly reduce the overhead, reduce the size of the proof. We might have all the things that we want straight up. So, and the next thing is something I thought was interesting. So the reason why machine learning became so prevalent and able to compete against privacy was MapReduce. So like, I call it optimistic compute paradigm. So optimistic compute paradigm is like, you send a compute load out, you wait for somebody to complete, and you trust them for being there to give you the result back, right? So this allowed, so Hadoop essentially allowed very large scale computations to happen and price discovery for machine learning in that sense. If that wasn't there, the bigger privacy challenges won't be there, right? So I probably might put my hand up and say, yeah, did some work over there, did some standards, but there's very little one could do on the other side. It is obvious what's going to happen. You can only watch and try guide it, but nothing much could be done. So I think this is going to be a race between the two sets of parties in that sense. One where there is a bunch of people who are really trying to run an arbitrage against society. So you could think of like I used to live in the UK, so we have a free healthcare system. So the classic case is cherry picking, right? So if you have any disease, you go to the hospital looks after you, right? Imagine you had a not so private situation where private entities actually look after sets of things and the rest is left to the government. Cherry picking would be easy because now you have a very clear idea of, And there are some entities based out of UK who have been accused of accessing data. I'm not naming them. You can Google them and find them. And you know who they are. So this is really scary, especially in a healthcare situation, looking at where the demographics is going. I'm just not just talking about DeFi. This is like all the way to healthcare and normal data, right? And the obvious statement is like, there is no such thing as free lunch, which is blindingly obvious. That's it, folks.
So basically, one of the ideas you conveyed is that the price of privacy is something that is not determined yet. And you're calling for protocols to have some kind of differential value of it. Do you think this will enable more participation?
So this is me thinking out loud, right? So what we need to understand is like, if the arbitrage is between privacy and privacy less, we lose the first place, right? We as protocol builders have to understand what is it that as a premium we are willing to pay. This could be dynamic, right? It could be that at certain situations, certain set of transactions have to have a higher privacy. And you have to do price discovery for privacy at that point in time and then provide privacy. Because providing privacy across the line, across the whole thing might not be the most efficient thing to do because it will increase the overall price of the protocol significantly and we won't be able to survive.
Also, you had a point about incentivizing people to participate as mining in helping those. Yeah. I understand how it can help with having more privacy, but does the flip side is also right? Like, if not enough people want to consume it, maybe there's some place to incentivize more participation as the consumers of privacy.
Could you repeat the last bit? I didn't hear the last bit.
Like you said, that such a protocol should incentivize people to be miners.
Yeah.
But is the opposite also true? Like if not enough people want to consume it,
privacy set will collapse. Literally will collapse, right? So it's like, imagine you have a Tor node, just one node. End of story, right? You shouldn't be browsing if it's just one node. So that's literally what is happening here. Thank you very much. There's no more questions.